Do you believe everything you read? Obviously, students have to know how to read before they come to your chemistry class. But you also have to teach them how to read something else in chemistry, and that has to do with measurement. And it's how to read measurements, whether it's on glassware, which is what we're going to look at today, or rulers, or if you have some other kind of instrument where you have to know how to read the scale. And so this activity is a very introductory activity for the first week, the first lab, the first day. You can do it as a demonstration. You can have students do it. And it's really to get them thinking about reading measurements and how to measure things and what we learn when we measure something. And then at the end, we're going to talk about the other importance of understanding uncertainty in measurements and error. So we'll get to that at the end. What I've set up here are 5 different types of laboratory glassware, volumetric glassware that we would use to measure volumes. I've got a burette, a 50 milliliter burette. I've got a 100 milliliter graduated cylinder, a 100 milliliter beaker, a 500 milliliter graduated cylinder, and 125 milliliter Erlenmeyer flask. And they're all going to give us different readings. We need to learn how to read measurements and in particular volumes. We're going to start with the burette, and I've simply filled it with some colored water. I simply took some blue food coloring and added that to water, just so that we would get a little color in this and it wouldn't just be colorless water in there. So I filled that, and I've already zeroed it on the top so that the upper level of the water there is exactly at 0, okay? And what I want to do is deliver 50 milliliters of water from the burette into the 100 milliliter graduated cylinder. So I'm going to go ahead and do that here. And burettes are precise because they deliver the volume slowly, so that's going to go fairly slow, but we're going to get it, try to get it at exactly 50. So obviously when I get down below here, I'm going to want to slow it down quite a bit. But we've got a way to go. You know, one of the first things you have to teach students about burettes is the fact that you're reading from the top down, because it starts at 0 on the top and goes to 50 on the bottom, as opposed to in a graduated cylinder where it's going 0 to 50 or to the maximum volume. So we're just going to take 50 milliliters out of the burette. And that's going slowly, but it you fill the time with a story. This, as I said, this activity is really going to be about error in science and the importance of error. And that may sound contradictory. What? You want errors to be important in science? And the answer is yes, from the point of view that you want everybody to understand the inherent error associated with any measurement. And that, I think, is a very important lesson in terms of doing science, but also for general public to understand what science can or cannot do. So there's a lot of sort of subtext to this very simple introductory demonstration that we'll discuss at the end. So I'm getting down here to, I'm at 45, 46, not quite as exciting as a countdown here, 47, 48, 49, and I'm going to slow down now just a little bit so that I don't overshoot, because I don't want to do that. And let's see, I'm going to just check the meniscus. This is a demonstration not about a titration, but just to be sure that we're good there, and I put a little mark there, and I'm going to go just a smidgen more. I'm going to take that last drop there. We'll have good technique. Okay, and we'll check that once again. And that looks good. So Laura's going to write down the measurements for us. We used a 50 milliliter burette, and I measured 50.00. let's take a look at, well, we'll do that later. So we're going to write 50.00 because on a burette, I've got major markings, 44, 45, 46, and so forth. But then I have minor markings at the 0.1 level. So I can see a line for 42.1, 42.2, 42.3, which means I need to estimate beyond the last minor marking on the glassware. So I'm estimating, obviously, that the second decimal place there in the 100th of a milliliter. So that was 50, and I'm going to take that out from under there. And now what I want to do, I'm actually going to move these all down just a little bit, is what I want to do is focus on the volume in that graduated cylinder. And when you can see that volume well, then I'm going to turn it around so that I can read the volume. Okay. And I'm going to use my card as well here, and I'm going to get down at eye level approximately. And what I want to do is read what it says and also what my uncertainty is. And I'm reading 50. Now here you've got to also look at what your markings are. And this is what the students have to learn when we said you have to teach them how to read. How do you read a graduated cylinder? The major markings are 10, 20, 30, and so on. So then the minor markings are 1, 2, 3, etc. And so I need to estimate in between those. So I'm going to get down again so that I can see that estimate. I'm actually going to do that down here. And I'm going to read that as... It's actually 51.0. Now there's the first thing. Well, it was 50. Now you're saying it's 51. What does that mean? Well, that's sort of the point of the demonstration. So I'm going to take from the graduated cylinder, and I'm going to pour into the beaker. And again, and now it is important to have good technique not to spill any. So having said that, I'm going to spill it. But let's try not to. And I want to try to obviously get as much out of that as I can, so I'm going to get those last couple of drops out of there. Again, because the point is I want to read the volume and I want to compare what the volume measurements are. So I think I got the last little bit out of there. And if you can focus on the volume reading in that beaker, and then I'm going to turn it around again so that I can read it, in fact, because we can't both read it at the same time here. Can you see it? You see the volume? Okay, if we've got a good shot of that, then I'm going to turn it around so that I can read what the volume is. And now, and again, I probably don't need this because this is way too much, but now my major markings are only 20, 40, 60, 80. Then there's a minor marking for 10, 30, 50, and so on. So if I do that, so I can only read it to really 1 milliliter, because I can estimate that since I've got, and that's a big estimate. So it's beyond the 50 minor marking, and it appears to be halfway between the 50 and the 60. So I can only estimate that really to 1 milliliter, and since it looks halfway to me, I'm going to say 55. So let's call that 55 milliliters. Boy, it looks like we're making more volume, doesn't it? Okay, you can kind of get the idea here. We're going to go from the beaker into this large graduated cylinder. And again, if you'll first try to focus on the level after I pour it, and then once you get a good, can see that, then I'll go turn it around so that I can see it. And again, I'm going to pour all of that, try to get those last couple of drops so that we model good technique here. Okay. And you can see that it's taking a little bit of time. Now we've got a 500 milliliter graduated cylinder, so as long as we're focusing on that, let's look at what the major markings are. We can see obviously 50, 100, 150, 200, 250, so on. And then there are minor markings in between those, and it looks like there are, actually it looks like there's two sets of lines, so there's a line here which would be, let's say, 125. So that means I can read 105, 110, 115, 120, 125. Is that right? Does that look right? Okay, so each minor marking is 5 milliliters. So if you've got a good shot there of the level, then I'm going to go turn it around so that I can read what it is. And again, I've got to get down because this is way down. Now this is interesting because this one actually looks like it reads slightly below 50, I would say. Let's see if we can see that. And if one marking is 5 milliliters, then I'm going to say it's about 49 milliliters. Okay. Finally, we're going to go to the Erlenmeyer flask. Okay. And I think you've probably got a good shot of what that level is reading. And let's turn it around. Now here, what are our markings? Our markings were 50, 75, 100, and there are no minor markings whatsoever. And not only that, but all of these pieces of glassware, they had a uniform diameter, cylinder size. Well, this one obviously doesn't, so who knows what I've got, but it's, let's go ahead and give it a shot. It's looks like it's above the 50, clearly below the 75. I have no idea what, but there's more down here. Since it's wider at the bottom, it gets narrower at the top. Oh, 60. 60 milliliters. Now, what's significant about these numbers? Well, obviously, they're all over the place, right? So the precision varies dramatically depending on the type of glassware that you're using. Now, let's estimate the uncertainty in each of these measurements. And so when we were reading the burette, we said that the minor marking was 0.1 milliliter, so we were estimating to the hundredth. So let's write plus or minus 0.05 because it's a very narrow level between each 0.1 of a milliliter. Some people say you can read to 0.02 with the burette. And you can. I'm not going to, who am I to argue with a textbook? But in practical terms, it's, is it 0.02 or 0.04? I think usually the best students will do is about 0.05. How about with the graduated cylinder? Well, with the 100 milliliter graduated cylinder, we had minor markings for every milliliter. That means we need to estimate in between there. And again, it's a fairly narrow thing, so let's say plus or minus 0.5 there. Okay. How about with the beaker? Well, with the beaker, we had 20, 40, 60, and then the minor markings was a 10. And so I can estimate probably, I'm going to say plus or minus 2 there. I don't think I can do plus or minus 1, but I can certainly do plus or minus 2. I'm probably being a little bit conservative here in terms of how well I can read all of these, but that's not a bad lesson either in terms of teaching students about measurement. With the 500 milliliter graduated cylinder, we said that we had a minor marking every 5 milliliters. And again, so probably there, I'm going to say again, it's about plus or minus 2, which is, about halfway in between 5, 10, 15. So you could see the difference between 7 and 9. You could certainly see that. With the Erlenmeyer flask, we really have no idea. I mean, plus or minus 10, because again, the major problem here isn't just that you don't have the markings so much as you don't have a uniform size. So you're truly there, you're guessing within the 10. So what's significant about reading volumes? I'm going to go to the board and look at these numbers and see what they tell us a little bit and talk about uncertainty in measurement. You know, a lot of students, when they do something in the lab, and I'm sure you have found that, they'll write down a number, and it's as if that number becomes gospel. You know, well, no, it was 52.6, you know, that exactly. We'll go, well, how do you know? What's your uncertainty? What's your error associated with this? With these pieces of volumetric glassware, the best that I can read, this 100 milliliter graduated cylinder, is plus or minus 0.5 milliliters. So if you're going to then use a volume to calculate something else as you go on, you're going to want to understand how that uncertainty, which is inherent in the measurement, we can't change it, how that will affect the final value that you calculate. So this really has to do also with significant figures. Students are always a little confused, I think, about the terminology of significant figures. It is one way to estimate error. Now, some people will argue that it's not really a good way at all, and you should simply always write down your absolute uncertainty and then calculate the relative uncertainty, and they do what's called error propagation. That's fine, but in chemistry, it's really a very good way to start understanding the inherent uncertainty in any measurement is with significant figures. How many significant figures are there in 50.00 milliliters? Because I've written the decimal place and I've written those zeros, those numbers are all significant. Remember, the last significant figure is the estimated digit. This digit was certain because we could see the minor level marking 4.1 milliliter on a burette. This digit was estimated. So you have 4 significant figures, and always the last figure is the estimated one. So here, 51.0, I have 3 significant figures because, again, I had to estimate between 51 milliliter and 52 milliliters, and I thought the best that I could do was 0.5 there. So you can see already I've got a 10-fold increase in the relative or percent error here. I've gone from, I have the same absolute volume approximately, or I did because I transferred it, right? But here my error has increased by a factor of 10. It's then gone up even more dramatically when I went to a beaker or to a larger graduated cylinder, and of course in the Erlenmeyer flask, all bets are off. So what does that tell you? Well, there's a lot of, as I said at the beginning, I think subtext here in terms of measurement. It's important to teach measurement. It's important to teach students about estimation. It's very important to teach them to always look at the glassware and to write down all of the digits that are certain and remember to estimate the last one. You will be surprised, and I'm sure all of you that have been teaching for a long time, you know, you do the titration, the acid-base titration, and they write down the volume of the burette. How many of you have seen students write down the volume of the burette was 49? And you go, okay, that's bad. That's very bad, because you didn't even bother to read what you could read, or if you did read it, you didn't write it down. So we said, what's significant about reading volumes? I suppose we could also say what's significant about writing down volumes and the importance of recording measurements. And they'll say, well, it was at the mark. I said, well, then you're supposed to write that down, that you could estimate it to that division and so on. This also tells us something about the type of glassware that you use, or, if you want to make it more general, the type of measurement device that you use. Obviously, if it's very important in a titration to know precise amounts of liquid that are added, well, you're not going to use a beaker because you're not getting any type of precision at all. So this significant figures and uncertainty in measurement have to do with precision of measurements. There's nothing in here at all about the accuracy, which is the correct value, unless we have calibrated or know exactly that the calibration, let's say the burette has been calibrated. That's our most accurate, it's our most precise, and if it's calibrated, we would know its accuracy as well, but we haven't done that here. We're just really looking at precision. You know, I said at the beginning that I think this has an important message in terms of understanding in some ways, and this is going to sound contradictory, the limitations of science. I think one of the things that distinguishes science from other fields is that scientists always report the inherent uncertainty in a measurement or in what they know. You know, a lot of people, well, I think such and such, and they just say that, and you go, well, how do you know that? Well, I just think it. In science, we report not only what we observe or measure and so on, but also it's important for us to realize and for us to expect scientists to report their level of confidence in a measurement, how well they think they know that measurement, so that we can understand. And there's a wonderful story that really goes back more than 100 years now, and it's Lord Rayleigh and the discovery of argon. Lord Rayleigh discovered argon in air. It's a very, very minor component. The way that he discovered it was by isolating nitrogen chemically from a pure compound, and also by isolating nitrogen from air and comparing the weights of what he got. And the difference when he obtained the nitrogen chemically versus from the air was less than 0.5% difference, and in terms of his measurements, less than about a milligram difference in weight. And the question is, was that significant? And the answer was yes. That milligram was significant because it said that the average weight, if you will, was different from the two, and from that he inferred that there was another compound in air which was increasing the molecular weight of nitrogen from air relative to nitrogen prepared chemically. He discovered that element in air. It was named argon. He received the Nobel Prize in 1904, a long time ago. But isn't that something about the precision and the significance of measurements that is an interesting story, along with maybe perhaps the boring parts of the measurement lab? So that's significant figures. I've tried to make it interesting, but significant figures are a struggle for many students. So thank you.